Oh, Rodrigo. Can anyone copy the link and then bring the link on the chat, please? Yeah. Oh, thank you for helping me. Then I'm gonna start on the today's session for variational autoencoder. So today we will cover the variational autoencoder practice with PyTorch. It seems similar to previous autoencoder practice. So I will assume that you've already knew the basic concept of autoencoder and the implementation. Also, since variational autoencoder is quite more complicated than autoencoder, so today's practice session assumes that you guys understand the VAE lecture materials by professor. Now let's begin with Jupyter Notebook here. So as I mentioned, VAE is based on the autoencoder. We will slightly make changes in codes of previous practice sessions. So the main points of today are understanding and the model architecture and how to make the code for VAE. The most important thing is the loss function of VAE. Yeah, like that. So I'm gonna explain about that. Yeah. Anyway, let's get into the code here. So settings, and before we move on to the main part, first import some packages like this. Some torch and torch vision, torch vision for MNIST image dataset, and then Matplotlib library for visualization like that. So I'm gonna import this one. And then among them, there is one additional packages like torch vision make grid. So make grid package is supported by torch vision utils packages. And it helps us make some grid style figures from like multiple images like that. So you can enjoy this for this session at the last part. And then from here, we will generate MNIST images from trained VAE. So we're using like that. And then hyperparameters here for this time are similar to the previous practice. Yeah, almost same. Like you can compare the code between the just autoencoder and then today's session code. Yeah. Of course, you can use the exactly same hyperparameters here, but you may use your own hyperparameter in the sessions. Yeah. Next step is data preparation. So the data preparation step is also same with the previous practice. So data set is split into train and test set first. And then the evaluation set is separate from the train set like this. So you can call the data set like torch data set, and then just like data set dot MNIST, and then you can automatically download the data set. And then like also if you know about the transform, like just for image augmentations, like to tensor means just get the images and not making that augmented, and then just make that at like tensor format. All right, then I'm gonna download it. So you may take some time to download this one. Yeah, I just already tried this code and then download the images, and then that images saved in the caches. So it skips the download step here. And then maybe everyone finished the download here, right? And then I'm gonna check the size of images here. And then for one image, the MNIST image have the 28 size here. And then you can check the label here. And then 2. So MNIST images consist of from 1 to 10 numbers of images. So the label is 2. And then I'm gonna set up the data loader here, and then I will skip the detail explain here. It's same as like the last lecture, right? All right. Here here is the image for VAE, right? One of the main interests is understanding and implementing VAE, the overall structure like this, and the process of VAE presented in this picture. So first, I'm gonna just briefly explain, like remind you about the last Tuesday lecture. So here we feed the input and the encoder, right? The encoder compress images into the latent vector, right? There is some encoder here, right? And then the latent vector is then decoded to generate images, right? Which should be as identical as possible to the original images, right? This is about the like reconstruction loss, right? We are using reconstruction loss for training the autoencoder, right? It is same here today, but a little bit different. I'm going to explain that. The sense of compressing the input images just is quite different from the like autoencoder here part. It includes input images in a stochastic way, right? So in other words, the probabilistic encoder tries to represent the input images into the following the Gaussian distributions. So using like mu and standard deviation like sigma like that. In this way, like encoder and decoder are not only trained to reconstruct the given images, but also to structure like given images space to follow the Gaussian distribution. Since VAE guides the input space to follow Gaussian distribution, VAE benefits to generate the image, which is different from the constructing given images. Therefore, one can generate the images only from the sampled values, like using the Gaussian distribution. Unlike these complicated theoretical concepts, implementation of VAE is quite simple and very it's similar to autoencoder. So feel free to like enjoy the code here. All right. Then move on to let's move on to the model part. Like we will implement the VA, right? VA, you're gonna build up on your variational autoencoder, and you can see there is some encode part here, right? And then the X would be input the images, and then you can see the encode model here. And then also there is decode here, right? So the output here, and then it seems like autoencoder, right? The input X, and then the input path feed to the encoder part, and then it pass through the reparameterize. So I'm gonna explain about that. Reparameterize, and then the latent vector will pass through the decoder and then making the image here for as a output. Here we use only the one like hidden layer and then a tanh, the activation function. The different thing we consider is like sampling process, which encodes the images into mu and log variance, like here. So it is implemented as like FC, FC mu and the FC bar like that here, respectively. And this is like, so I'm gonna show you like self.fc mu and then fc barrier. Bar means variance, right? So you're gonna use this one, right? You can see the initialization part. Now we can try to implement this part like variational autoencoder style, like not like just autoencoder style. After you implement by yourself, we can keep going to the next step. So just it's like just guessing the dimension on here. So please fill in the blanks here, and then just I'm gonna give you some hints here. Is the encoder and the decoder module is quite simple, but you may wonder what are FC and then mu and epsilon, right? So here, as the encoder has two layers, right? And then 10 dimension size output vectors, the mu and log variants are implemented like this. So and then the forward part is here. You will understand the mu and log variants will be passed through the model with reparameterized things. So to sample the latent vector z, right? So finally, the latent vector z will be given to the reconstruct the images which are similar to input images, right? Then what is the reparameterized method and why we do this? Like we will not cover details on this part on this practice session, but simply we can think about this as for making encoder part as stochastic and enable to use backpropagation to optimize the optimal objectives. So now you can implement reparameterized method here. So like it's time for DIY, so doing yourself. So I will give you 5 minutes and then you can refer this one and then yeah. And then the last lecture, like let's fill the question mark here. So I will give you 5 minutes.
I'm sorry to interrupt you, but I think there's a new question in the chat.
Oh, all right. I'm gonna check that. Chang-hun asked the questions like, why do we get log variance instead of log standard deviations? What does that mean? Variance. Could you explain more detail about this, please? I'm guessing that like
I don't know his exact intention, but I think because the variance is the square of the standard deviation, so I think his intention was maybe we can just get something like log standard deviation term instead of getting log variance, I think.
I got it. I think I don't know the difference when we use the just log variance and then or instead log standard deviation, but maybe both options can be possible for training. But I don't know the exact reason for about why we have to choose the log variance and then like that. So there's no exact reason about that. Don't know the exact like answer about that. You can use like log standard deviations. Yeah. Yeah, both options are trainable, as long as far as I know. So everybody have done with this? If you need more time to implement this, like you can follow this just code the solution after the lecture. So I'm gonna show you the solution here. Like 28 multiply 28 is like 256, right? So here, and then the FC mu, the linear layer, we get 256 return vector right here, and then it's gonna have the output size 10, same as for FC bar, right? And then the decoder will get the output size 10, and then make the 256, and then 256. Everyone got why we take the 28 and the 28, right? It's image size, right? So here, and then the for the reparameterized part is kind of like some tricky part. So you may felt this part as like tricky part, right? So here is like this, and here is the random Gaussian. Random-like, do everyone know random-like? Random-like means that make the Gaussian distributions, but it will make the same size with like the target tensor, like this. So this is the solution for the question mark, right? All right. I think everyone followed this code, right? So yeah, right, finished. And then let's move on to the other part, right? Actually, like this, like standard deviation is like just kind of math. Like the epsilon is a sample value from the like normal distribution. Like why we 0.5 multiplied with standard deviations. 0.5 is the like exponential. 0.5 means like scale root, right? So it will be the standard deviation, right? Is it right? Right? Right. All right. So I'm gonna move on to the last part, the other parts like loss function and optimizer. The main, the other part of VAE is like loss, right? Loss is the main part, the difference between the autoencoder and the VAE. So the loss function of autoencoder was just a simple like MSE loss, right? To measure differences between the original images and reconstructed images. So similar to that, VAE loss also includes a reconstruction error defined by binary crossover entropy. So before I move on this loss part, I'm gonna check the device first, and then all right. And then here we see loss. Binary cross entropy can be computed easily by using PyTorch module like this. And then we will use the summation reduction mode to make implementation easier, right? So, all right. And then the other loss part is the K divergence loss part, which is regularization term, like to make the variation distribution, like to be similar to the Gaussian prior. So if you follow well on the lecture notes and take care about the reduction term of BC loss, then the code implementation will be like this. So you can use MSE also. So I'm gonna introduce why we are using the BC loss here. So then the KLD loss, like K divergence loss, will be here, right? You can check this code and then we can compare this code and then the equation on the lecture. Then here, then the model we defined here, right? So I'm gonna use that and then move the model parameters to move GPU, right? And then optimizer using all right, sorry. Optimizer, we are gonna use Adam optimizer. And then the training code is fully implemented here. So it is almost same with the PyTorch trainer, like routine codes, like just here is for loops for epoch, and then here is like data split mode, like train eval mode, and then gonna have some mini batch training here, right? Then here the model here, and then the model inputs will the output is like outputs means like generated images, right, from the autoencoder part, and then mu and log variance is gonna use for the KL divergence, right? The outputs will be used for the reconstructions. So so right, first of all, right, as previous practice, we can check whether VAE can reconstruct the input images or not. So now I'm gonna train this here, train mode. So I'm gonna train this one here. It's gonna take some time. All right, loss decrease well, right? Well trained. Jiyoung asked a question. Running loss. Could you explain more about running loss? What is running loss? You mean reconstruction loss or could you explain about the what is running loss? Sorry. Here, this part, right? You don't need to take the input size, like it's the intention for about that is like multiplying the sample size, right? But here the BC loss have the reduction option as sum, so it automatically sum all the loss of the samples loss each. So is it right? Uh, Maybe, yeah. The last session, I didn't do the last session, so uh, I don't know the detail about that, but maybe I guess, right? The reduction is mean, so for the last session, so maybe gonna take the multiplying the input size, like the batch size, right? I I don't know the exact why the last session used that. So you can check that maybe. All right, yeah, cool. So let's see. Then training finished, right? So everyone have read it about this. So now let's see the reconstructed and then original images here. First we're gonna plot this like the loss decrease well. So we can see here, right? So check the test images here. First the loss here and then check the images here. All right. So the left images is the real one, what we feed to the model, right? And then the right part is generated images from the VAE, right? This is from the like reconstructed. So someone Sungmin asked the question, why do we use BC loss function instead of elbow? It's elbow term is on Kell divergence loss, not on the BC loss. BC loss is like I'm gonna explain more about that, but for the autoencoder, maybe it may use that at the last session MSC loss, right? But instead of MSC loss, then we just use BC loss here. So it's not BC loss is not related to the elbow, actually. It's about the Kell divergence loss. All right. All right, it's fine, right? So here the cases of the digit 1 and the 4 are reconstructed well, but I think it's quite a bit confused with like 5, right? Or this should be 3, right? But it seems like 8. So it is quite a bit confused here, right? The 8 and then 5. The quality of generated images are poor here. It's not that poor, but I mean, like for the case of 3 here. So and then other qualitative method to evaluate our VAE is visualizing the encoded input images as plotted here, like the autoencoder sessions here. So I skipped the detailed visualization. Code is same as like autoencoder sessions. So. Gonna have some time. All right, and then put this. So 10 digits are like separated well on the feature space, like we trained VAE. So I just show you the two methods, like just how to check the VAE is trained well. Like first, just check the visualizations for the images, and then visualization the feature latent vector is like this scatter one, and then here the third one is to like this, and then we're gonna you can check how the images are clustering here like that. And then the third method to evaluate VAE is generating the MNIST images only from the sample to latent vectors. The case I showed you here is just visualize the reconstructed images, but here I'm gonna use the latent vector as an input and then really generate it from the just some distribution to the images. So here, so I'm gonna check encoded shape. So it's very interesting to observe how the generated images changes through the latent space traverse. So first of all, we leverage the encoded feature vector of train subset since we already checked the VAE. So I'm gonna check here. So it's successfully encoded, right? So each digit is separated well, and then we calculate the many feature factors of each digit from the encoded feature factors like this. So then walk through the latent space between two digits means the mean of feature vectors, right? In our case, I selected two digits class, 7 and 1 here. And then, to be more specific, we interpolate these two mean feature vectors in the case 1 and 7, and then generated images from trained VA decoder like this. These generated images, I use the make grid here, right? So make grid packages from the torch visions. And then you can change the selected class and then not only just 7 and 1 and make more observations on the traversal of latent space. So I can give you some 2 or 3 minutes to change this traversal, not just taking the 7 and 1. Yeah. You can use this one, 5 or 6, this. Oh, 5. It seems quite weird here, right? I cannot recognize which one is 5 or 6. Then 6 or 8. 6 or 8. Like this. All right. These interpolated images indicate our BAE successfully project the input space to predefined prior, right? The Gaussian distribution. So also roughly speaking, one can say that BAE learns visual semantics rather than memorizes them, from 6 to 8 like this. All right, this is same code. 1 8, and then note that considering the above model is low capacity model, we just use just one or two, right? Maybe one frequency layer, right? So let's say the model with one more linear layer will have some high capacity. So you can compare the VAE performance at low capacity and the performance at high capacity. So here is you can may fill this one, and then it have one more linear layer here. So you can do that doing yourself. And then this is the last part of today's lecture. So I'm gonna show you this part. So for image A is the original image, and then the B and C is like reconstructed images. What I'm going to explain about you is like BC laws and then MSC laws. Like you may use like MSC laws instead of BC laws. That means that just roughly speaking, each pixels have the pixels original the values, right? Pixel values. Then if you're using the MSC loss means that you will get the loss comparing the generated images loss the pixel values on that position between comparing between them and then between the original images pixels, right? So if you use the MSC loss, if your image generated image is B, then this part is errors from like original images like this, right? This is MSC loss. You can see that the C have the more like similar values, this part, right? The white space part. But if you use the BC loss, that means that it will gonna have the it will gonna take the loss as like classification loss, right? The autoencoder model will gonna take the gradient direction for like making the get right choose like from between 1 to 10 digits, right? So what I mean is like if you use the BC loss, the model will take the semantic meaning of this like amnesty images, not just like just pixel to pixel comparison like MSC loss. And that is the difference between using the BC loss and the MSC loss. So everyone got it, what I mean. So maybe there is some papers, yeah, like this person. I forgot the exact paper title, but you can search about that, about this. I forgot to explain about that. Sorry. Yeah. What is different from B and C is like the one or two pixels shifted to right images. Then all of the pixels have different values from the images A, and then B is just erase this part. I read about this and then remind about that. Yeah. Yeah, this is the just rearranging here or shift all of the images on the orbit right part. Then if you use the MSC loss, then C have much greater loss than B. The B has just different part is here, the erasing part, but C is all of the images shifted to the right part. So in the perspective of pixel values, the C has really different values from A. So when you use MSC, then the B images has a lower MSC loss than images C. But if you use BC loss, then C is more smaller loss, right? that kind of things. So anyway, the lecture is finished here, right? And then, any questions? Thingy. Thingy say about the why do we need 0.5 with standard deviations, right? Here, standard deviation and then torch dot exponential like 0.5, then multiplying log variance, and then 0.5 exponential 0.5 is like square root, right? It seems like it's exponential, but I mean how can I say that? If we have some like exponential calculations, like Hangers replied about that. Like, all right, and then why can we get FC mu and the FC bar with one linear transformation? You can use different things. You can use different things, but it's like you can use different models, not only just one linear transformation. Here is just example. So just the simplest one is like frequency layer. So you may change this, like output size also. And then if you change this encoder part, not just like 256 to 256, and then it's like then, and then you can use this and then like that. Yeah. All right. All right. If you don't have any questions, I'm gonna finish the session here. So thank you for listening for today.
감사합니다.
All right. I will upload the solution code on Classroom.